Okay, so now we are going to talk about K-means clustering. Again, here we are importing all the stuffs, right? Again, we are also using some other library called Yellow Brick to visualize the the performance of models. Again, we'll talk about the scale visualizer and silhouette visualizer, right? Now, what we'll learn in this lecture. So basically, we'll see what is unsupervised paradigm is, what are the motivations and potential application of the clustering algorithm we have. We'll also define the clustering problems. Right? We'll also broadly explain this K-means algorithm and apply this K-means algorithms using scalars. We'll talk about pros and cons and the K of the K-means. We'll also talk about what is elbow plot, what is silhouette plot, and how to do that. We'll see the idea of GMM model and how this GMM, which stand for the Gaussian mixture model, how this GMM is different from the K-means algorithms. We'll talk about this covariance types hyperparameter of the GMM. We'll also explain this model selection in the GMM, and then we'll also discuss about what is the difference between soft clustering and hard clustering. Yeah, so again, we have a lot to discuss. Let's get started. So now, here, consider that if you have to pick, like, let's say that if you have to kind of categorize this item based on the breakfast, right? So based on the breakfast, we can categorize like this could be as a one category, this could be as the another category, this could be as the another category, right? And let's say that if you have to categorize based on the food and the desserts, so food is this sorry, this is also a desserts, this is a desserts, right? This is a desserts, right? These are the desserts, this is the desserts, right? So again, we can categorize these foods with the various aspect, right? We can also categorize based on the salad and not salad. Like this looks and salad, this looks and salad, this looks and salad, right? We can also categorize based on the calorie count. So the question is, we have the data, right? But consider that we do not have any category of the data. But as a human being, we can categorize this data in a various way. We can categorize this data as in desserts and non-desserts, right? We can categorize as a data with a high calorie and the low calorie. We can categorize the data with the salad and no salad, fruits and no fruits, right? So we can have a much more category, right? This is totally up to us how we are understanding the data, how we want our data to be discretized or to be separated. Right? Now, in clustering, most of the data are so when most of the data are not labeled, that means so you have just the data. Like over here, we have just the data and the labels what this specific thing is, but we do not have any type of category or any type of numerical value for this data. We just have the data, but now we want to make sense of this data. Now, if we know from where this data is coming from, if we know where this data, in which industry, in which application this data will be used for, based on that, we can categorize this data very effectively, right? And that categorization task, though we do not have any category, but as a human being, we have to understand how we are categorizing the data. Now, that is called the unsupervised learning. That means in unsupervised learning, we do not have any labels. We do not have the Y value, but we want to categorize these value, right, as per the business requirement, right? And for that, we use a very different techniques. So as a motivation, most of the data is unlabeled, right? And mostly getting the label data is very difficult. So the question comes as, can we extract some useful information from the unlabeled data, right? Can we extract like whatever the unlabeled data is, can we extract whatever the information we want to extract? So the thing is, if we know the business, if we know the data, so we can extract the data very effectively, right? And the most intuitive way to categorize the data is to group the similar things together. Now, this is totally up to us how similar we are understanding. Are we understanding, let's say that over here, are we counting the calorie? Like high calories should be in one group, other low calories should be in another group. Are we counting as a salad and non-salad? Like this could be in salads, this could be a salad, this could be in salads, right? Are we saying that as our desserts and non-desserts, right? These are the desserts and these all are the non-desserts, right? This is totally up to us how we want to categorize, and that understanding we get from the business, from in which business we will use this technique. So all in all, clustering is a task of partitioning the data into groups. We call this as a cluster, and this data partition happens based on the similarity. So for example, let's say that here if you want to categorize all, like if you want to categorize based on the desserts and non-dessert, so category of the dessert, like this is the dessert, these are the desserts, right? This comes as under as a desserts, right? So category of the desserts, these are the desserts, right? So category of the desserts have the different features, right? And category of non-desserts has a different feature. So we'll have to understand how we are partitioning the data, and that partitioning is happen based on the clustering algorithm. So here our goal is to cluster the groups, cluster the data into groups, right? And the examples belonging to the similar groups will have the similar features. The example belonging to the different groups will have the different features, right? Now to understand that concretely, here we have these examples where we are getting a data set. So this is a data set, original data set we have, and here we have not labeled any data set. So here there is no label of the data set. But when we look at the data on the graph, we can simply see that these examples are close together. That means they are similar. These examples are close together, and so these are the similar, these are the similar, and these are the similars, right? So based on that, here we have labeled these examples, right? Now, so here, one way to think of the clustering is a task of coloring the given set of points. Here we have the points. So we have colored all the points which are close together. So these examples has been colored with the red. This example has been colored with the blue. This example has been colored with the green, right? So usually the clusters are identified by the cluster labels, right? So here, this red, blue, green is nothing but a labels, right? So we can label these values. Like over here, we can label these data points as in one group, this data point as an another group, and this data point as an another group. This could be the cluster labels, right? And here, these labels are arbitrary, right? And relabeling the point does not make any sense, right? So if you switch the label, let's say that instead of saying group 1, we'll say group 3. This would be group 2 and this would be group 1. That is, so doing this, changing the label does not make sense, because here the real knowledge does not comes under the grouping, because this grouping is what as a human being we are making the group, right? But in reality there is no such group given. So it's like, even though if you change the label, that does not make sense. So these points should still be in the same groups, right? But what we care is the point in the same groups should have the same labels, right? The point in the different group will have the different labels, right? Now, in real world, this is just a toy example. In the real world, this is rarely happens, right? So rarely we'll get this kind of data where we'll separate all the data points very effectively. And now consider these example over here. So here, consider that this is the data we have. This is the data we have. And we have the data of emojis, cat and human, crying and happy. And this is the first categorization that we are doing. Here the first categorization we are doing is these emojis belong to cat and these emojis belong to human, right? So the first division, let's say that someone has told you to divide this data. You will divide this data based on the emojis of cat and based on the emojis of humans, and there is no problem in that. So we have divide this data in a correct way, but we can also say in this way. So here all the groups, all the examples are happy, all the examples are unhappy. Now this category, this grouping is still makes sense, right? There is no problem in this grouping. So we cannot say that this is the correct one and this is the correct one. We cannot say that. Both are correct over here. So in real world, this thing happen, right? We do not decide what is the correct grouping. But what we want is, we want all the data in a group should form a cluster. That means all the data in a group should be very much close to each other. If it is happening, then that considered as a correct grouping, right? Now, what are the applications of this kind of uh, algorithm we have? So the first application is as a data explorations. So although there is not any right answer over here, like over here, we did not have any right answer, right? You might still get something useful out of clustering. That means there are some number of applications for the clustering we have, like we can summarize and compress data. We can use data compression in the clustering. We can partition the data into groups before further processing. So before processing, we can partition the data and then we can partition each group uh, in a different way, right? We can also do the customer segmentation, like over here. These are the executive groups, these are the retiree, right? So we can group different kind of persons, right, in a separate category, right? So this is called customer segmentation. We can also use clustering for the document clustering. So so this clustering that you see in the Google photo, in the Google News, right? That clustering happens because of the Kmeans clustering algorithms. So K-means clustering have are like so not only K-means, so any clustering algorithms. So clustering has a lot of application in the real world, right? There are the other applications we have like social network analysis, medical imaging. We can use clustering for imputing missing data, data compression, privacy preservations. We can use clustering for the anomaly detections. There are a lot of applications we have for the cluster, right? So now let's understand about the K-means clustering. Now, K-means is what? K-means is one type of algorithm for clustering techniques, right? So here, clustering in K-means, clustering is based on the similarity or the distance between point. That means if two points are close together, both can come under a one cluster, right? Or a similar things are close together. This is the thinking, this is the notions we have in the clustering. Now the question comes as how do we determine how do we determine which points are similar together in multidimensional space? Now we have already discussed these kind of problem. We have already discussed like k neighbor algorithm for the similarity, right? In the k neighbor, we have used the Euclidean distance to find the nearby points. We can use the same idea for the clustering over here, right? So here K-means is one of the most common used clustering algorithm we have, right? Where the input is the X is the data points and K is the number of cluster we want to build. So in K-means we have to give the two values as an input, the data itself and how many cluster we want to build in this data, how many cluster we want to create from this data. As an output, it will give you K clusters or K group of the data point. Right? Now, first, let's implement K-means algorithm using sklearns. So before understanding the algorithms, let's try the K-means. Here, consider these toy examples we have, right? Now let's try K-means algorithm on this data set. So first we have to decide how many cluster we want. Now here, by looking at the data, we can simply say that this data has the three clusters. Now, when we call the fit method, it only need the X of the data because this is the unsupervised technique. We do not have the label value over here. We do not have the Y value over here. So here we have imported k-means. In the k-means, we are saying n cluster equal to 3. We are saying n init equal to auto. This we have created the k-means. We are applying fit method over here on the X data. This means that now we have trained the model. Now when we call k-means.predict, this will give you the predicted labels. Now which label? Basically it's a group label. So it says that 0 example belong to the 0 group, first example belong to the first group, second example belong to the second group, third example belong to the first group, and so on and so forth, right? So now all these example has some index. Now every example belong to some group and these groups have become labels. We can also get the labels after we apply the predict. We can also access these labels with the label attribute. We can call dot labels. This will give you the label for each examples. And here we have assigned all the labels for the specific data point. Now this data point belongs to label 0, this data point belongs to label 1, and so on, right? Now in k-means, each cluster is represented by its cluster centers. So here k-means have a cluster centers. So let's say what are the cluster center of these examples we have, this data set we have. So when we call this cluster centers, right, here we can see that these are the cluster centers we have for three groups. So how many cluster centers we'll have? So let's say that if you are building a three groups in a cluster, if you are building a three cluster, so you will have the three cluster centers, right? So cluster center is nothing but the middle of the clusters, right? Or like centroid of the clusters. Here we can simply predict, here we can simply print the label of the cluster. We can see that this is the label of cluster 1 according to that. So this has automatically labeled this as a cluster 1. This is the cluster, the star is the cluster center of the label 2, and this blue point is the cluster center of label 1, right? So this is nothing but a centroid, which is the average of all the data points. This become a cluster center. So with the fitted k-means, we can also use predict on unseen example. We can simply call, let's say that here we have this new examples. Now we can apply predict method on that, on this new example, and we can simply predict the like here what we are saying is we are just trying to plot these examples over here, right? So this is the first example we have, this is the second example we have. By looking at the graph, we can simply say that this triangle belong to this group 1, and this triangle belongs to the group 2, right? But let's predict it. So here when we do predict it, we can simply say that group 2, okay, so this is the first examples. So the first example belong to the group 2 and the second example belongs to the group 1, right? And here we are labeling those examples with their appropriate groups. So here we are coloring those examples, right? Now, what are the main idea of the K-means algorithm we have? So the main idea is we represent each cluster by its cluster center, right? So here in K-means, we represent each cluster by its cluster center and assign a cluster membership to each point, right? Like these example belong to the cluster 2, so it has assigned these all this example as an, so it has given the label as a 2. These example belong to the cluster 1, so this has labeled these example as an label 1, right, or a cluster 1. So now the question comes, if we know the cluster center, we can simply assign each point to its the nearest center. But here we do not know the cluster center. Similarly, if we assign a new like if we knew the assignment, we can simply calculate the cluster center. So we do not know the assignment either. So the question comes as an, so we do not know the cluster centers and we do not know the assignment. So this is a problematic we have. So how we can solve this? This is a problem of chicken and egg problem. Now when this kind of problem arise, we usually use the iterative method. So what do we do here in Kmeans algorithm? So uh, in K-mean clustering, we have seen that the input we need as a data, right, and the number of cluster. First, we initialize the K initial centers for the clusters, right? So the first step is, right? So we initialize K initial centers. Let's say that we want the three clusters, so it will initialize three centers. And then it will repeat these steps. So assign each example to the closest centers. And then after that, we estimate a new centers. So basically we find the new centroid, the average of all the clusters, right? That is how, that is how like this thing happens iteratively until we do not change the centers, right? Or until we reach to this maximum iterations. So this is how the K-means algorithm looks like. So here we are executing this K-means algorithm on our toy data set. So let's see the data point we have. So these are the data point we have. The number of example is 10. Here we want the three cluster in this data point. So first we'll initialize the K initial centers. So here we are initializing. So this is like before clusters, before clustering, and this is like after clustering. Here we have initialized the three centers. So randomly we have picked the three centers. So this first one, second one, third one. Now remember this centers have been picked randomly. Now the next step is we need to find the new center for all the data point based on the closest centers. So again, remember, after after we initialize the centers, we assign each example to the closest center and then we estimate the new center as an average of all the observations, right? So here it will update each example to the closest center and we'll call this as an update Z and then we'll update the centers. This will happens until we do not reach the centers. So here we have created this function. So here at first we have this three centers. Now we are changing the here this 1 2 3 means we are changing the different iterations. Now in every iteration we are changing the new value. So here we are changing the different points, right? And here we are calculating the distance over here, right? Now we know how things happens. Right here we have created a function called update z to update the center to assign each example as a centers. And here we have created another function to call update centers, which update the centers after we assign each example to a new centers. Like after we assign each example to a new uh, uh, to an to its new center, right? So after I find it, we'll update the centers based on finding the average of all the data points, right? So here, this is the functions we have, right? And this is the this is like first initial centers we have. After that, here we have created. So here we have like here we can see that at iteration 0, the z is this, right? So first we have updated z. That means we have assigned each example to the closest data point. Like this data point has been assigned to this center. This three data point has been assigned to this center, and so on, right? And then here after that we are updating the centers. So here the center of all three data point will be here. Center of all these data point will be here. And here we can see that at after points, like again, we cannot just calculate. So this like, but again, like if you run this code, right, what this will do is basically this will happen like update all the value, right? Now the question comes when to stop after iteration 4, just like here when to stop. So here we had stopped after 4 iterations, right? So after 4 iterations we have stopped changing the value, right? And why? So here we can see that this centroid has moved to this centroid, this centroid has moved to over here, and this centroid has moved over here. So every iteration, this new centroid is, or like a new center is getting changed, right? And this will change until we do not reach to the optimum value, right? Now, so this is how a K-means algorithm works. A comment on initialization. So initialization of K-means is stochastic and can affect the result. Like over here, we can look at this example over here, right? And when we initialize our data point into three clusters, so what we see over here is these. So this happens during the initial kind of initializations, right? But here, after so many try, what we find is this center has not, so the center for this data point has not been changed. So basically, this data point has only one center, like this center has only one data point, right? And this example has moved from here, like from here to here. And this example has moved from here to here. But literally, we can see that this is one group, this is a one group, and this is another group, right? But this thing is not happening because of bad initializations, right? So how do we do that? So again, we can use like if we initialize our algorithm in a more appropriate way, like over here, we have initialized all three centroid in its kind of appropriate place. Then after 5 iteration, we can see that we have updated our centroid into its optimal way. So for that, we have to change something into the initialization parameter, right? And that algorithm is called k-means plus plus. But it seems like when we apply the scikit-learn k-means, it internally it also uses the k-means plus plus only, right? So internally, this scikit-learn k-means is nothing but k-means plus plus. Basically, they use smart way to choose the optimal or like smart initial k value, right? Now, what is the objective function of k-means? Now, so here we have to find the local minimum of we have to find the local minimum of minimizing the square distance. So here, so the algorithms optimize the sum of the distance of cluster center to all the data point to that cluster. So what do we do? Basically, we try to calculate the distance between each example with its own clusters, right? And then we take the sum of that, right? And like, and like that is what this algorithm does, right? So in other word, like if this distance is minimum, right? If this value is minimum, so that we have reached to the to we have reached to the optimal value. Again, this is so in other word, it minimizes within the cluster, right? Sum of the square criteria. So within the clusters, we try to minimize the value over here. Here, u is 1 if the point xj belong to I, otherwise 0. So basically, U is deciding which point belongs to which clusters and nothing much, right? Here C stands for the clusters. So basically, this is an NP-hard problem. That means we cannot find the optimal value at every situations, right? So for that, we have to choose a different techniques to find the optimal key value, right? Now, why we should not use the gradient descent, right? So basically, this is an iterative approach, right? This is the iterative approach. First, we need to obtain the centroid, and then we need to change the partitions, right? So here we cannot use gradient descent because gradient descent try to minimize the value, and there is no such thing over here in this algorithms, right? Now, how do we calculate the which distance function we can use? We can use the L2 norm function as a distance functions, right? And yeah, So LT norm is nothing but the Euclidean distance we can use to find the distance between each example to its own clusters, right? Now we can also do feature engineering using K-means. So basically sometimes we have the examples, sometimes we have the group even, but now let's say that we want to group things together. For that we can use the K-means algorithm. We can use a K-means to kind of group different example, right, into the multiple groups, and then we can create a new feature. Now that new feature will be used, will can play an important role during the during the supervised learning. So in that way we can use a feature engineering over here, right? Again, these things are optional. We're not going to talk about this time complexity of the k-means, right? So now the question comes, how do we choose the k-means? So basically here choosing k is the hyperparameter, right? That means when we run the k-means algorithm, we have to specify how many k value or how many cluster value we want in a data, right? In supervised learning, we do find hyperparameter using cross validations. But since in unsupervised, we do not have the target value, so it becomes difficult to find the effectiveness of the algorithms, right? So there is no definitive approach we have. So however, we have some strategy to choose the different k value, right? Here we can use the elbow method. So elbow method is what? Basically, again, the name elbow method comes because the way it looks like, right? Like when you plot the data output onto the graph. Now, this method looks at the sum of intra-cluster distance. So first we need to look at the sum of intra-cluster distance, which is also referred to as inertia, right? So first we calculate the inertia, right? So intra-cluster distance on our toy example is like over here. So what we are doing is, so now this intra-cluster distance means we calculate the data point belonging to to some so here we calculate the distance between the data point and its own clusters, right? So first we calculate the total distance between the all the data point to its cluster, right? And that is what the inertia is. So here we calculate the inertia. Here all the c is nothing but the centroid, p is the point value, and the distance is the Euclidean distance that we can use, right? So now the question comes, how we can access this inertia centers, like inertia clusters, right? So here to understand that we have created this example. So this is the data point that we have created, right? Now we can access this inertia value, right, by using this inertia attribute. So here we are building models. We are trying for different k. Now we want to know for each k, what is the inertia value we have, right? So here for different k, we have the different inertia value. And what we see is like as we go over to the maximum k value, the inertia value has started decreasing, right? Now the question comes, which is the best inertia value, right? So the inertia value decreases as the k increases. So how do we want, like, do we want the inertia value as a small or large, right? So the problem is that we cannot just look at the k value that minimize the inertia because it decreases, the k increases. So here, this is the like here we have to choose based on some technique, right? One technique is we can use elbow method. Like over here, we have created this function called plot elbow, right? So here we are just using for every inertia, what is this, for every k, what is this inertia value is, then we can check the plot. This is the function that we have this, and here we can see this. So for every k value, what is the different inertia value over here? So here we can see that like for k value as well, the inertia value is very much high. For k value is 2, the inertia value is still high, but for k value is 3, inertia value is very close. Now after this, there is no significant change in the inertia value, right? Like there is no step change in the inertia value. So we want to find this point from where the change is mm, very much low compared to this drastic change. So we'll choose this as a k. So here we'll choose 3 as a k value, right? Now, now you do not need to remember how to create this elbow functions, right? We have this function called yellow brick, which will help you to kind of plot this k elbow visualizer. So to plot this elbow plot, right? In yellow brick, we have to import this K elbow visualizer, right? Here we have created the model. We are passing this K elbow visualizer. We are trying a different K value. And now we have to apply fit at this method. Right here we can see that at this point we can see that this is the giving us the output at K elbow at K value 3. The score is 186 and this seems to be the optimal K value where this distortion score, we call this as a distortion score, is very much low, right? Now here we are trying our, so yeah, so here is again like how do we do that? So here is again a method we have, right? Now we'll talk about the silhouette method. Now in silhouette method, which is not dependent on the notion of cluster center. So the silhouette method does not depend on the cluster centers, right? It is calculated using mean of intra-cluster distance and the mean of nearest cluster distance. What is meaning of this? So here, so first we'll see what is mean of intra-cluster distance. So suppose this green point is our sample data points. This is our sample data point, right? And the average of the distance of green point to other point in the same clusters, right? Here, this green point and these all this black point. If the distance between that and when we take the mean of that, that is what the mean of intra-cluster distance is, right? How do we calculate the mean of nearest cluster distance? So now to find this mean of nearest cluster distance, we take the average of the distance of green point, this point, to the blue point, this point, is smaller than the average of the distance of green point to the red point, right? As we know, the distance between, so the average of all this point distance and average of all this point distance is, so the smaller is this blue point. So the nearest cluster is the blue clusters. So this blue cluster is our nearest cluster. So the mean of nearest cluster distance is the average of the distance of green point to the blue point, right? So this average is called the mean of nearest cluster distance, right? Now, so this silhouette, the distance depend on this A and the B part. So the silhouette distance is the difference between the B minus A divided by max of A and the B. So the again here we are normalizing this B minus A value by max of A by B. The best value is 1 and the worst value is -1, right? If we'll get 0, this means that we are getting the overlapping clusters. So our task is to get the 1 as a value in the silhouette score, 1 as a score. Now, how do we use this silhouette score to select the number of clusters? So for that, we can use this plotting functions. We can use this silhouette visualizer, right? And here we are using this silhouette visualizer, and here we can see this. So here we can see the two clusters we have in this. Now, now as in again, I have said that the silhouette score is greater than, so like if this silhouette score, this red line is our silhouette score, average silhouette score. If this average silhouette score is higher side, then we are making a good cluster. So our task is to achieve this silhouette score as high as possible, right? Here we can see that here we have created a two cluster in this. Let's say that we are creating five clusters. So when we create five cluster, our silhouette score is 0.5. In the two cluster, our silhouette score is 0.7, right? And in the three cluster, our silhouette score is 0.8, which is higher than all. So now we can say that here we can say that our best k value is the 3. This is how we look for the silhouette score, right? Now we'll talk about Gaussian mixture models. So again, we'll talk about GMM at very high level. Now this K-means is great, but it cannot handle oddly shaped clusters, right? So in K-means, our clusters are defined by the cluster centers. Here we have this data set. We have created the three data set, right? And here we have stacked all three data set in just one data, right? And here we are looking at the data. Here we can clearly see that when we visualize it, we can clearly see that we have the three cluster in this data. So one is this, other one is this, and the other one is this, right? Now this is the very odd shaped cluster. So this the shape of this cluster is totally different. Shape of this cluster is different than the shape of this cluster as well. So now what will happen if we'll use Kmeans cluster on this data set? So here we know that we have the three cluster. We are using the n cluster as 3, right? And when we check the labels after we plot it, here we'll see that. So what do we see? We'll see that these examples belong to one cluster, which is not true. These example belong to one cluster, which is also not true, and these example belong to one cluster, right? Which is somewhat true. But here we can see that because of the centroid and because of this its centric nature, right? It is not able to capture the oddly shaped clusters, right? So it can capture only the cluster with the circular shape more efficiently, right? So here the K-means is not doing a good job. So one limitation of K-means is that it only takes into account mean of data point and not spread of the data point. So K-means does not consider how the data point is spreaded, right? Now, how about taking into account the covariance matrix, right? So here, the covariance matrix will give you how spread the data is, right? And basically, when we use, so Gaussian mixture model is nothing but considering the different components of the covariance matrix, and that's the reason it's called the mixture Gaussian mixture models. So here in this Gaussian mixture model, so we want to model the data as a weighted sum of Gaussian distribution of the data, right? So here we want to model the weighted sum of Gaussian distributions where each Gaussians referred to as a component of mixtures, right? And has its own mean vector and covariance matrix. So each component will have their different covariance matrix and different mean vector and their corresponding weight as well, right? Now these models are referred to a mixture of Gaussian or Gaussian mixture models, right? Now here, let's try to use this Gaussian mixture models. Here we are saying this, we want to have this three component and we predict it. So after the prediction, we can clearly see that here we are using the covariance type as full. We'll talk about that later on, what is this full means. And when we do this, here we can see that this is what we get from the k-means and this is what we get from the GMM model, Gaussian mixture models. Now we can see this Gaussian mixture model works great, right? So clustering with GMM are better, right? It captures a different shape compared to the K-means clustering. We can also check the mean of the GMM and the covariance as well. So we can check the mean and the covariance vector of the Gaussian mixture models. And We can also check the weight of the each component. So weight means basically it gives the this component has lesser weightage and this component has high weightage, right? When we do submit, you will get the value as in 1. So now, how does it work? So again, we'll talk about at high levels, right? So given k value, the number of cluster or the number of component, right? So k is what? The number of clusters, or we can also say that we want to find the different number of component. We want to fit the Gaussian blob to the data, right? And each Gaussian will have its own mean vector and covariance matrix. So whatever the, like, let's say that here we're saying that we want 3 components, so it will fit 3 Gaussian vector and the the 3 different covariance matrix, right? So this is a generative models. This is called a generative models, where it models the probability of given data point being generated from the mixture of Gaussian, right? So we get the probability of different data point, like how each data point is belonging to which mixture of Gaussians, right? Here, X is a data point. This pi of k is the weight of component, right? Here k is the number of cluster, mu of k is the mean vector of the component, sigma k is the covariance matrix. Again, there are a lot more we can understand with the mathematical, but we not go into the mathematics, right? But just understand that Gaussian mixture model is able to handle the different shape of the data as well, right? Now here, how to interpret the weight associated with the Gaussian? We can see that here the phi we can see as in the like over here uh, with this. So we have this phi 1 and the phi 2, which is the different components, right? And this is the different functions we have, right, with the different mean value and the covariance value. So this is the weighted the value that we are getting, right? So here we can see that. So this blue line is nothing but a mixture of models. And then here we have the two function. We have this function and this functions, right? Now we want to find the mixture of these two functions. So here we are getting the mixture of these two functions, and the function 1, which is this, has the mean 0, right? Function 2 has the mean of 0.5, right? And the weight of the function 1 is 0.5 and the weight of the function 2 is also 0.5, right? So when we say, like, we want to give, like, when we want to give the weight as 0 for the function 1, so this the mixture function will only learn this functions, right? Like when we give the more weightage to to kind of mixture 1 or like function 1 and 0 weightage to function 2. Here we can see that this blue line has learned these functions. So we want an intermediate function which can combine these two functions as well, right? So here we can see that here in this, our weight parameter is higher in the function 1 and the lower in the function 2. So we want to have a such functions where we can achieve maximum from both functions, right? This is how a mean function decides. So this is how mixture model uh, we create, right? So our goal is to estimate the pi, which is the weight, the mean, and the covariance of all cluster or the component K. Right? Again, it is a non-convex optimization problem, so it is sensitive to initializations. Right? Right? Generally, we used with the soft assignment. That means each data point has some probability being in class or being in cluster one, and the other probability being in cluster uh, two, right? So this is how we use. Again, this is an EM problems, but again, we are not going to discuss this EM optimization algorithms. Now we can constrain the covariance of the Gaussian by using covariance type, right? Now, when creating a Gaussian mixture model, this allow to control the shape and the complexity of the cluster. Like over here, we are saying the covariance type as in covariance type. So here we are trying a spherical, the diagonal, tied, and the full, right? So this is what happens when you use the spherical. This is what happens when you say that you want to capture the diagonal of the data. This is what happens when you want to capture the tide of the data. And this is what happens when you want to capture the full of the data, right? Now, since GMM have the soft clustering assignment, we can predict the probability that if a given point, we can predict what is the highest, what is the probability of what is the probability of point 1 being in cluster 0 or being in cluster 1, right? Here we are creating so this is the data frame we have, right? And here we are applying the predict, like here we are trying to get the probability score for this 10 data point, and here we can see that like with this full covariance matrix, right? The cluster, the example 0 belong to the has highest score in the cluster 0. Example 1 has the highest score in the cluster 0, and so on, right? Now we can also check the score here. We can check the score, which gives us the log likelihood of the value, right? Now it is possible to do the model selections, right? We can use AIC and the BIC criteria to kind of select which model is the best model, right? And how do we do that? Like over here we have this multiple component we are trying a different models, and then for every model, here we are trying to get the AIC and the BIC score, and then we are plotting this AIC and the BIC score over here. Here we can check that this is our BIC score and this is our AIC score. Now, both AIC and the BIC score is very much lower at n component at component 3, right? Here we are trying a different component. We just want to find how many number of clusters we have. So at component 3, we have the lowest AIC in the BIC score. This means that this means that our optimal k value or our optimal n component value is 3, right? We can also use this example with the grid search, right? Now, as in summary, right? So what we have discussed the clustering, which is a common algorithm for unsupervised, which is common unsupervised technique, right? We did discussed what clustering does. We did discussed which algorithm we use, right? We did discussed K-means is the very popular algorithms, right? Now we have also discussed clustering with K-means, right? We did discuss how to choose the different the best K value, what is elbow method, what is silhouette method, right? In what situation this K-means algorithm gets failed, how do we initialize a different K centers, right? What are the optimal way, like what is K-means plus plus we have discussed. We also discussed about the Gaussian mixture models. We discussed about it has the different covariance type. That means the different covariance type is like spherical, diagonal, tied, and the full, right? And we also discussed that this, like in the GMM model, each example can have a different like each example can have a different assignment, right? So each example belong to the cluster 1, cluster 2, and cluster 3 with the different probabilistic models, right? And now we have also discussed about how to calculate AIC in the BIC score, and based on this AIC in the BIC score, how to pick the best component, right? And yeah, that's it. Thank you very much.